Alrighty, so here we are in Ksp. Ksp is kind of a specialized version of equilibrium. The general idea, before we get into specifics, is that you have a solid compound being dissolved into water. We don't typically even show the water because it is always in water. And as that solid compound hits the water, some of it's going to dissolve into its ions. Unless it's otherwise stated, we always assume that there is no initial ions in the solution. Now we'll have some other scenarios and later problems in just a couple minutes where there are some initial chlorine or lead, but in this first question there's no mention of any lead in the water, there's no mention of any chlorine in the water. It's just how much lead chloride will dissolve into water in terms of grams per 100 milliliters. So I did a little bit of the whole rice table thing. I have the reaction and the initial values, so R reaction, I initial, change in equilibrium. But because it's so simple, a lot of times pieces just kind of get snipped off. So you have a solid as your initial. You have no ions in the water. Some of the solid is dissolving or dissociating. And so there's only one lead per compound, so you have X quantity, but there's 2 chlorines, so when it dissolves, it's going to give off 2 chlorines, or twice as much chlorine as lead. If we take these values, well, let's first, here would be the expression, Ksp would be equal to lead times chlorine squared over 1. It's over 1 because the lead chloride on this side is a solid, and solids are always represented by 1 in these expressions. If I take these two x values and plug them in there, I would have x 2x squared, which simplifies down into 4x cubed. X represents how much the compound dissolves. They have in this question given us the Ksp, so I plugged it in, then I solved. But the problem with this answer here, this is the first answer I get, is that's in moles per liter of how much lead chloride dissolved. That's molarity, moles per liter. And the question specifically says to convert it to grams per 100 milliliters. So I'm going to just do some dimensional analysis and convert it over. So here was the moles per liter, changed it using the molar mass of lead chloride, and then liters to milliliters, and I got this answer. Oh no, that's grams per 1 milliliter. I want it per 100. So there would actually be 100 times more. So I multiplied this number by 100 to get it to be grams per 100 milliliters. So that's how many grams of lead chloride would dissolve into 100 milliliters of water, which is a pretty common volume. We usually use 100 milliliter graduated cylinders or beakers, things like that. So about a half a gram of lead chloride would dissolve in, which is not much. Unless you're drinking it, that's a problem. Number 2 is a similar scenario. We have some calcium carbonate, and it's being put into water. I'll just throw this on here. It doesn't actually impact the reaction other than it's causing the dissociation to occur. And some of this compound will dissolve. So we'll make some calcium, we'll make some carbonate. Notice these are coefficients of 1, so you get an equal quantity of both the calcium and the carbonate. Where here the coefficients were 1 and 2, so you get twice the chlorine. So it's 1 to 1, so you get 1x and 1x. If we plug these x's in to the expression, x times x is x squared. Now, in this question it gives the solubility, and solubility is a way of saying how much will dissolve in terms of moles per liter. So if the solubility is given, they're telling us how much dissolved. They're telling us how much dissolved. So we know the value of x, so we can plug that into our x expression as x squared, and we can solve for the Ksp. And now we know the equilibrium constant for calcium carbonate. So number 2 is kind of the reverse question of number 1. What else could they have done to give this part harder? They could have, instead of giving x in terms of molarity, anytime we go to these Ksp KSP expressions, they need to be in terms of molarity. What if they had said, there are 2 grams of calcium carbonate, I'm just making these numbers up, completely dissolve into 500 milliliters? Well, they'd be telling you the solubility in a roundabout way. You'd have to change these grams of calcium carbonate into moles, divide by the volume, then you would know the molarity. Now these are fake numbers here, so it's not going to work. But again, you have to have X in terms of molarity, so you could change the grams per 500 milliliters backwards into molarity. Number 3 is a different scenario. In number 3, there's silver chloride and there's hydrochloric acid, both being mixed in the same solution. Hydrochloric acid is one of those strong acids like sulfuric or nitric, and that means it completely dissolves, 100% dissolves. You could think of it having a very, very large KSP, maybe not a million, but a very large KSP. So all of its hydrogen and its chlorine dissociates. So if you have, in this case, 0.02 molar hydrochloric acid, this compound's really not together. It's actually splitting apart into hydrogen ions and into chlorine ions. And these hydrogen ions are doing some stuff with water we're not getting into right now. But so for every 0.02 molar hydrochloric acid, you're going to have 0.02 molar chlorine floating around in that water. And if there's already chlorine in the water, that's going to impact the other compound, the weaker compound. The silver chloride is not very good at dissolving, at least compared to hydrochloric acid. So we would have to throw this value for chlorine in at the initial, there's our I for initial, in for our initial concentration. And then as this compound dissolves, some of the solid's going to dissolve. Some of the silver's going to be made. Going to get some chlorine, but we're adding X to an existing value. If this was not here, if this term wasn't here, that X value would probably be a lot larger, but it is there. So it's going to impede silver chloride's ability to dissolve. The basic KSP, can't speak. The basic KSP expression isn't too drastically different. It's silver times chlorine divided by 1. But then we'd have to plug in these equilibrium values into those two positions, and we end up with X 0.020 plus X. We have to solve for X. And there's 2 very different approaches for solving for X. One is actually, there's 3 different approaches. One's doing the algebra as we solve for using the KSP value that's given here. 2 is using the solver function. You would use the solver function. You would plug in your boundaries as 0 and the maximum possible quantity for X. And in this case, you would have to say, you'd use KSP is equal to X squared to find the max value. As if this term wasn't here, you could figure out the maximum value for X. And so we take a square root of 1.1 times 10 to the minus 10th. So that would be, let's say, like 1.1 times 10 to the minus 5th or something like that. So those would be the boundaries you would use in the solver function approximately. You really need to take a true square root of this number to find that other boundary. And the third method is a realization kind of method, that if KSP is this small, it's not going to be able to shift very far to the products before we achieve this value. We're going to get tiny little values for X. And what is a tiny value of X plus 0.02? It ends up still being 0.02. So it simplifies the math down. You can get rid of that X term. You can get rid of this X term and just use 0.002 for the chlorine. And that's what's going on here. I said KSP is equal to X times 0.002 plus the other part's been removed. So it's easy to solve for x. And what's funny is if you use this method, where x is incredibly small, or you use the solver function method, you'll also get that same value. Now, you might have a different, this is 5.5 times 10 to the minus 9. Maybe yours is 5.5027. I mean, it's just different 4 or 5, 6 sig figs down, but not at a point that impacts the real math, the scientific notation, sig figs, and all those things. So the real issue here, let's talk about the real focus of this. If there's already an ion in the solution, that's going to impede the compound's ability to dissolve. This is called the common ion effect. Number 4 is another example of the common ion effect. There's 2 compounds dissolved in the water. The one that is already dissolved in the water is the aluminum sulfate. And aluminum sulfate must dissolve really well because its molarity is 0.1 molar aluminum sulfate. So let's just this isn't really how I would do this, but let's just run through it. 0.1 molar aluminum sulfate completely dissolves. So there's no more solid left over. It dissolves all the way. The solid's all gone. You'd be making 2 aluminums for every one of these that dissolve, so you're going to be, x is going to be 0.1. Well, 2 times x would be 0.2. You're making 3 sulfates. So for every 0.1 of these compounds that dissolves, you're making 3 times the amount of sulfate. You can really just think of it as the aluminum and the sulfate are breaking apart in 5 different directions. A sulfate, maybe an aluminum, and another sulfate. And so for every one of these that dissolves, you get 3 sulfates. Well, in this question, there's 0.1 aluminum sulfate, so there's 0.3 sulfate in the solution. I probably just made that much more complicated than most of you would do. I would have just said to myself, there's 3 sulfates, this is how much dissolved, I'm going to multiply that by 3. So how does that impact the silver sulfate? So this sulfate is already in solution. It's going to impact how much sulfate is in the solution. So what? Well, the silver sulfate, that is a solid, is going to try to dissolve, but there's already sulfate in there, so kind of like the previous problem, it's going to inhibit the ability of the silver sulfate to dissolve, and it's not going to go all the way. We have our Ksp expression in terms of x's. Here's Ksp. I assumed x to be insignificant compared to the 0.3, and I solved for x, 3.41 times 10 to the minus third. Then I used the solver function, just because I know some of you love the solver function. So I did 3.040 times 10 to the minus third. Those are the same value. I know you're looking at that going, that's a 1, that's a 0. Those aren't the same value. But this value wouldn't be written down. We only have 2 sig figs here. So really, they are both 3.4 times 10 to the minus third molar. So they're really the same thing. So that's the value for x for both compounds. That is how much silver sulfate would dissolve. If I plug that in for silver, 6.8 times 10 to the minus third would be the concentration of silver. And then the concentration of sulfate would be 0.3034 sulfate. A pretty small quantity. 5 and 6 are whether or not a precipitate would be produced. And so the way I think about these is you have these ions, and if we have too much silver and phosphate, or if we have too much lead and iodine, it's going to push the reaction this way, and a solid would be formed. If we have too much lead and iodine, it's going to reverse the reaction and make a solid. And the Ksp value represents that balancing point between the two. So they tell you the value of lead, and they say how much iodine would you have to get to push it backwards. So I just real simply plugged in the Ksp value was equal to the lead times the unknown iodine, and I solved for that value, and I found that if iodine equals this, you're right at the equivalence point. If iodine equals this, you're right at the equivalence point. So if it exceeds it, it's going to precipitate, it's going to push it backwards. Same thing down here. If you have too much silver, it's going to push it backwards. And so when the silver is equal to that, you have reached the equilibrium point.